All right, good morning, everyone. Welcome to today's online class. So how are you today? Hope everyone is staying at a safe place. So for this class, since due to the weather conditions, so we will hold it as an online class. But the recordings of this class will still be released afterwards, so don't worry about that. So before we start, I would like to make a short announcement that the Lab 2 has already been released. So as you can see, so with a few minutes, I will share my screen first. Yeah, as you can see in the course website, here, Lab 2. Of course, if you are LA1 students, then actually already took the Lab 2 yesterday. Here, Lab 2 is released here, and again, we release the review notebook so that you can have a review of the naive classifier. Afterwards, we have the lab work. I know that since Lab 2 is a graded lab, so that means you need to submit it on Zinc. So for Lab 2 submission deadline, it will be on October 8th. So that will be like next month. You will have like around 3 weeks to finish it. So if you have any question regarding this Lab 2, you can contact our teaching team, especially Lab 2 is maintained by our TA Pengbo here, as you can see. So if you have any question, you can just ask. Of course, you are also welcome to just ask in Piazza. The online platform to ask questions. You can post your questions or any of your thoughts there, so that all of our teaching team and all of our classmates can help to address your questions. All right, this is about the Lab 2. And next we will start today's class. By the way, during the whole online class, if you have any question, you can either raise your hand on the Zoom. So yeah, I think there are like some effects, things like that. Let me see. Yeah, I guess you can just directly select to raise hand in the Zoom bar. And also you can always type your questions in the chat box. So I will also check this chat box frequently. And if you type any question there, I will address them. All right. So today's class, we will continue with the naive base. So recall that in last class, we finished introduction of the basic concepts of machine learning, including supervised learning and unsupervised learning. Then here, I would like to invite you to think about a practical problem like this. So now suppose we have a data set. This is our data set basically in this table. This data set consisting of symptoms and also the results showing the patient suffering from disease Z or not. As you can see here, in total, we have 14 data samples, 14 rows here. And there are 4 symptoms like blood pressure, fever, diabetes, vomit. So if we try to abstract this data set into a supervised learning problem, then actually probably we will see that actually this data consists of 4 features. Like each of the symptom is one feature, right? And this last column, whether this patient suffers from disease Z or not, actually is a label. Like for each data sample, we already provide the correct output, the label in the last column. So of course, it should be a supervised learning problem. All the data points are prepared with the labels. Now here is our practical problem like this. So given this training data, we want to do some prediction, or we want to apply it to a testing data. That is, can we estimate whether now a person suffering from disease Z based on the symptoms? But that is, now we come a new patient. The new patient with these 4 symptoms, like blood pressure is high, but no fever, and has diabetes and has some vomit. Okay, based on the new patient symptoms, we want to predict whether this person suffers from Z or not. And note that if you check the table here, actually there is no data points that have the same feature like this, right? So basically that is to say this testing data is a totally new data for our model. Because this model has never seen such a data in training data set. Then can we try to do such prediction? Yes, by using Bayes rule. So next I will introduce about what is the Bayes rule. To start with Bayes rule, the very important concept is the conditional probability. So here let's review what is conditional probability. So conditional probability usually we denote as this one, like the probability P of an event B given another event A. So this conditional probability means what the probability that the event B occurs given that event A already occurred. So if we check the mathematical formula of conditional probability, we can get that this conditional probability PB given A actually equal to such a fraction. Like first we need to get the probability of both A and B happens. That's PA and B. Then divided by the probability of the event A occurred, that is divided by PA. So that is that we first count like, okay, with what frequency or what probability that the event A or our condition A will happen. And then we also need to count like what is the probability of like both A and B happen together and then get such conditional probability. So here is an example. Look at this data. Of course, this data is totally made up. Okay, we just use it as an example. It doesn't mean that it's some real statistics. So suppose we have like UG students and PG students, and for each student, the student can choose to go to the campus by car or on foot or by bicycle. And suppose the statistics are like this. So that is in total, we have 650 UG students, 650 PG students, and also for each of the transport method, we get the statistics. So then what is the conditional probability of P car given undergraduate students? Then by the mathematical formula, we know that, okay, we should first get the probability of car and UG students. That is the probability of any UG students take car to campus and then divided by the probability of UG students, right? And we know the probability actually, in reality, it comes from the event counts. So basically, the probability is such a concept that it tries to estimate the frequency of some event happening. And such frequency is exactly coming from the event count. Or equivalently to say, we just need to count the number of corresponding events. Then we count, okay, the event counts of car and UG students, actually we know is this entry, right? There are 200 UG students who take car. So the numerator thing, we should put 200 here. Then the denominator thing is the count of all UG students, which comes from this entry, so 650. So that's why we can get, okay, this conditional probability is 200 over 650. Similarly, I believe you can all get this conditional probability, like the probability of bicycle given PG students. So again, we check the corresponding event count, like the PG students taking bicycle is this entry 80, the total number of PG students is here 650. So that's why we get the conditional probability like this. All right, so yeah, hope you have the like clear understanding of what is a conditional probability, because this is the basis of the Bayes rule and later on the naive Bayes classifier. Then we introduce what is the Bayes rule. Here the Bayes rule is named after 18th century British mathematician Thomas Bayes. Yeah, just this guy, as we can see here. Note that the Bayes rule is the most important rule in data science. Actually, until now, it's still the most important rule. Even though actually it's already very old, we know that like it has like hundred years of history, but still the most important rule. So it is a mathematical rule that describes how to update a belief given some evidence. Okay, now some new terminologies occur. Let me illustrate. As you can see in this formula, we have like two symbols B and E. So usually we call this E as evidence. Evidence, know that in machine learning model, evidence is exactly the feature. So feature of a data point is some evidence, like in observation. And here the B, we call it belief. And know that in machine learning model, this is exactly the class in classification problem. Like the data point belongs to some class, which is equivalent in the statistic that some events has corresponding belief. All right, so we have the two terminologies, E and B, evidence and belief here. Then what is this Bayes rule? Basically, Bayes rule is trying to tell us how to compute such a conditional probability, the probability of a belief given an evidence. And this is exactly from PB, the probability of this belief times PE given B, this conditional probability, like evidence given belief, then divided by the evidence probability. And know that actually here for each of the four probabilities, we have corresponding terminologies to describe them. Like this one, this is what we want to get, is called the posterior probability. So posterior probability is how often the belief happens given some evidence happens. Now that usually this is what we want in a practical problem, or you can consider in a machine learning problem. Of course, usually we want to get like what is the probability of a class given the data features, right? This is typically the prediction in machine learning, posterior probability. And then what is this one? The probability of the belief itself is called the prior probability. It describes like how likely the belief is on its own. Then another conditional probability here, PE given B. This is likelihood. Likelihood is how often the evidence happens given that the belief happens. And last, the probability of the evidence itself, we call it marginal probability, is how likely the evidence is on its own. Yeah, I know, like these names may like seem unfamiliar to you because possibly this is the first time that you know all of this terminology term. This is by conventional, we call these probabilities, these names. And now the Bayes rule gives us a way to calculate posterior probability. So that means in the practical problems, usually what we are given are these three things. Usually is that we are already given the prior probability, the likelihood, and the marginal probability, and then we need to calculate posterior probability. So let's say an example so that you can know how to apply Bayes rule. Suppose now our evidence is smoke, right? The smoke is like something we can observe, it's the evidence. And the belief B is fire. So we want to know whether there is a fire or not. And then the prior probability, PB, is like priorly how often there is fire on itself. Marginal probability, PE, is how often there is a smoke. Then the posterior probability, PB given E, is how often there is fire when we can see smoke. So that is, we already have the evidence, and then what is the conditional probability of the belief? While the likelihood, PE given B, is how often there is smoke when there is fire. So Bayes rule is such a formula trying to tell us P fire given smoke when we already know the P smoke given fire. And suppose we already know all this information, know that these three information must already be given to us. Like if not, otherwise, then we cannot predict the posterior probability. So these three things must already be given to us. Like we already know that, okay, dangerous fires are rare. Like for example, with 1% frequency, so we can know, okay, now this prior probability PB is 0.01. This is already given to us. And we also know the marginal probability, like we know the smoke. The evidence itself is fairly common due to some other activities, for example, the barbecue. So the marginal probability PE, which is 0.1, we also know this number, and we should also know the likelihood, of course. So we know, okay, now 90% of the dangerous fires make smoke. So that is to say, given that there is fire, then the conditional probability of smoke is 0.9. Okay, after knowing these three probability numbers, we can use the Bayes rule to estimate the posterior probability. So that is, what is the probability of dangerous fire when there is smoke? Directly applying Bayes rule, we can see that, okay, it should be P fire times P smoke given fire divided by P smoke. And after replacing all these terms using the numbers, we get that, okay, this posterior probability is just 0.09. That is, if all this information are correct, like all these three probabilities are correct, and then we can see, okay, now whenever you observe a smoke, then there is 9% probability that there is a fire given your evidence, given your observation. So this is the example, like how to apply the Bayes rule. Okay, so until now, any questions so far? If any questions, so please feel free to type in the chat box. Then the next thing is, okay, we already know the mathematical formula, we know an example, then how to understand the Bayes rule. But here we try to visualize it using a tree structure. Okay. When student asked that why it is not just P fire divided by P smoke, this is directly from the definition of conditional probability, because the conditional probability PB given A, actually, like by definition, it should be the probability of both A and B happen together divided by PA. So P fire given smoke, actually it should be P fire and smoke, and then divided by P smoke. So basically, we need to apply the Bayes rule here. And the Bayes rule actually is not hard to prove. So that is, if you already have the definition of the conditional probability, basically you can prove the Bayes rule by yourself. And actually we provide the supplementary notes. So as you can see here. Yeah, so if you're interested, you can check the supplementary notes of naive Bayes, like a proof of the Bayes theorem. And it's not hard, you can also try to prove by yourself. All right, yeah, hope this can clarify it. Then continue with like how to represent the Bayes rule using some tree structure. We draw this tree structure, and here is a root node here. Like, do you know what this root node means? This root node means everything. Every possible things, we put it at the root node. And then what is the probability of every possible things? It's 1, right? So basically the root node here, if we make some nodes, we see, okay, here is a root node. We use this root node to represent every possible things, and of course the probability of every possible things is 1. That is the meaning of the root node. And then if we check like every possible things, then basically we can divide every possible things into 2 cases. Because now we only care about our belief B, so we just divide it into, okay, it's either B happens or not B. right? For any possible things, we just can separate into these two cases if we only care about B. Then for this edge, it represents the probability of the belief B happens is PB, while this one is P not B, like not B happens. Of course, we know PB plus P not B equal to 1, like equal to this root node probability. Then if we further consider evidence, like we also care about whether the evidence happens or not, then for each of the node here, like B and not B, these two nodes, we can further divide it into two nodes. For this B, it's either like E happens or E does not happen. So we further split it into two branches like E, not E. In this case, note that now this edge is associated with a likelihood, the conditional probability of PE given B, because it's split from this node. So that means when we reach this node, B already happens. And we further want to get the likelihood, we further want to get the conditional probability of like E also happens. So that's why this edge is associated with PE given B. And similarly, for this edge not E, it should be associated with such a likelihood P not E given B. Then for this node not B, again, like we can just further split it into these two branches, like E happens or E does not happen. And for each of these edges, we associate with corresponding conditional probability. So basically, we can try to visualize the Bayes rule using such tree structure, starting from every possible things, first split into the beliefs and not beliefs, and after that, split into the evidence and not evidence, and so that we can get all the possible cases with all the corresponding likelihoods. And now let's check one thing. Let's check all the cases where E happens. And we find that if we just look at this tree structure, there are only two paths from the root node to some leaf node that representing the E happens. That is, here is one path. So starting from the root node, we go this way until we reach this node E, right? Basically, it's the blue path here. The second path that E happens possibly is starting from the root node all the way along until we get this leaf node. There are only such two cases that E happens. And according to the total probability rule, we can get one thing is that, okay, if we want to get the probability of E happens, basically we need to add up the two possible cases. The first case, like starting from the root node, go to such a leaf node. So that is PE given B times PB. So that is all the probability. We need to multiply them along the path to get what is the probability of reaching this node. Then for the second path, again, we multiply all the corresponding likelihoods and prior probability like PE given not B times P not B. And then we reach this leaf node with such probability. And since the two paths all lead to E, so actually the PE is the addition of such two multiplications. All right, actually until now, possibly it makes some sense to you that why this PE is called marginal probability, right? So it just sum up all the possible cases to get the probability. It's like doing some marginal calculation. So that's why this PE is called marginal probability. Actually, after you see this formula of calculating PE, maybe you will get some more insights. So what if in some problems, we only know the likelihood PE given B, and this likelihood PE given not B, and we also know the prior probability PB, P not B. Suppose we only know these things, but we do not know the marginal probability itself. Can we still apply Bayes' rule to calculate posterior probability? Yes, we can. Like actually this PE marginal probability is not necessary to be directly provided, because we have such formula to calculate it, PE. So if we already know these four terms, then basically PE can be calculated. So still, we can calculate the posterior probability PB given E. Like this side, the rightmost side is the original Bayes rule, but somehow we can substitute the PE with such formula so that still actually we can get what we want. So let's see an example. It's about the virus detection. So now a doctor gives a patient a test for a particular virus. It is believed that 0.1% of the population has this virus. And note this information, 0.1% of the population had this virus. What it tells us the prior probability, right? So suppose this virus, we call it V, then basically this sentence tells us one thing, is that UV, this prior probability equals 0.001. This sentence tells us such an information about the prior probability. And let's continue to look at what we have. Based on experience, the doctor knows that in 99% of the cases in which the virus is present, the test is positive. What does this sentence tell us? Likelihood, right? So basically it tells us some conditional probability, like in which the virus is present. This is a condition and the test is positive. It's a conditional probability. So given this sentence, actually we get another information about likelihood, is that, okay, we know that this probability of positive, test positive, we just use this plus to represent positive, given the condition of the virus is present, equals to 0.99. This is the information. And continue, in 95% of the cases in which the virus is not present, the test is negative. And note that this is another likelihood we get, right? So for this sentence, it tells us such information, that is, this conditional probability of the test is negative given that the virus is not present. Virus is not present, we call it like not V. And actually later on you will see that we use another symbol to denote not V. So suppose we just call this not V as H. Just use H to denote this not V event, then we get that, okay, this is 0.95. So this is the two sentences. Basically, this graph told us such information. And here the question is, if the test turns out to be positive, what is the chance that the virus is present? Or equivalently, this question asks us to calculate the posterior probability. The posterior probability P of the virus is present given that the evidence test is positive. So what is this? So after looking all of this information, basically we get this prior probability, likelihoods, and we understand, okay, now this question is exactly asked to calculate posterior. Can we apply Bayes rule to solve this problem? Let's try that. So we use these denotions. Actually, I just introduced V means the part of the population carrying the virus, and let H be the remaining part. And basically, this is already what we summarized. So we know PV is 0.001, and this one actually tells us another information about the pH, because for the population, either have the virus or not the virus. So basically pH must be 1 minus this PV, which is 0.999. And we also get the two likelihoods, just the information tells us, and we want to calculate posterior like this. Let's try this, okay? We know according to Bayes rule, PV given plus should be PV times P plus given V divided by P plus. Of course, we already have PV. We also have P plus given V. Then what is this marginal probability P plus? Look back at that total probability of PE here. We know how to calculate PE. right? So just apply such formula here. We know that P plus actually should be P plus given V times PV. This is the first case that is plus. The second case of its being plus is P plus given H times PH. So we just try to add up the two possible cases and we can get the marginal probability. And note that now P plus given V, we already have it from the statement, is 0.99. PV, we already have it, is 0.001. And P plus given H, although we do not directly have it, but still we can calculate it by just one-step calculation. Recall, we know what is this P negative given H. If we already know the condition is H, and we know after the condition is H, the test is either positive or negative. So basically the P positive given H just should be 1 minus P negative given H, right? Because they must add up to 1. So here this P positive given H is exactly 1 minus 0.95. And this PH, we have that. We already calculated that. So that means for all these 4 terms, actually we have the corresponding number. So we can calculate what is the probability of P positive or this P plus. After that, we can estimate the P virus given positive using the Bayes rule, because now all these 3 items, we already have that. Estimate that it's approximately 0.02. So this tells us the conclusion that even though if any patient or if any person has the test positive, but actually the probability of that person having such virus, this probability is quite small. As you can see, the probability is only like 0.02. Or you can see that this test is not so accurate. This test is not so convincing. Like even if you get some positive results in such tests, still the probability of like you're having such virus is very small. It seems like counterintuitive, right? But actually it makes much sense, because if you consider what is a prior probability of such virus V, it's only 0.001. So here the true reason is that this virus itself is very rare. It's very, very rare happening. Like the prior probability of such virus is already small. But that's why like even you get the positive test result, still the conditional probability of such virus is small. This is what we can get from such example. So any question regarding this example? If you have any question, just let me know, type in the chat box so that I can always check that. Here, let's try to extend the problem to a more general case. Don't be frightened by such tree structure. Actually, it's a directly extension of the previous tree structure. Not hard to understand. Let me try to explain. Here is a case. So what if we have multiple pieces of belief? This is typically the thing, right? Especially if you consider that in machine learning problems, usually we are doing multi-class classification. And each of the belief B, actually we know is just a class of the classification problem. Of course, usually we want to deal with the multi-class classification instead of like some binary classification. If we look at the previous tree structure, the belief B can only be B or not B. Basically, it's like binary classification. There are only 2 classes. It's either positive or negative. But the typical case is that we have multiple classes. Do some multiple category classification. So here it corresponds to like the multiple pieces of belief. Still, this root node is everything. The probability of the root node is 1. Then starting from the root node, we can split every possible things into n cases. Like the belief B can be B1, B2 until Bn, or equivalently, there are n classes. And for each of the edge is associated with the corresponding prior probability. Like this one is associated with PB1, the prior of B1, and this one is PB2, the prior of B2, right? So on and so forth. Then under each of the node, we can further split it into two branches. So again, it's like the E. This evidence E, it either happens or does not happen. So like if under the node B1, it happens, then it's the likelihood of PE given B1. And if not happen, E does not happen, then it's the conditional probability P not E given B1, and so on and so forth. So basically, we just directly extend the previous tree structure into such multi-pieces of belief cases. Then what can we gain from such a multiple belief case? Basically, now we try to get a new form. It's not really new form because it's still is the same with the previous form, but somehow it's a more general form. Like now, for each of the belief BI, we want to get its posterior probability. This is what we want always, like PBI given E. If we directly apply the previous Bayes rule, we should get that. So this PBI given E, of course, it should be PBI, the prior times the likelihood, like PE, given BI, then divided by the marginal probability, PE. So this is the direct Bayes rule, right? And then the numerator is still here, like PBI times PE given BI prior times likelihood. But the denominator, like what is the marginal probability? The marginal probability, again, we try to apply the total probability rule. So in this tree structure, we try to find all the possible cases that E happens. And we find that in total, there are n possible cases that E happens. First is that given B1 already happens, E happens. Second is given B2 already happens, E happens, so on and so forth. The last case would be given Bn already happens, then E happens. And the next thing is we just add up all the probabilities of these n cases and get the marginal probability PE. So here PE should be something like this. PE given B1 times PB1. That's the first pass starting root node to the leaf node E. The second case is PE given B2 times PB2. And so on and so forth, we just add up all the possible n cases probabilities. And in short, we can write the equivalent formula like this. Numerator, of course, is still PBI times PE given BI, but the denominator here is just we use this sum symbol, the sum of PE given BJ times PBJ. Here J should be from 1 to n. And now each belief BI is called a class. It's just some multi-class classification, right? Like if we look back at the previous virus detection problem, like here in that problem, we have two classes. Like V is the population carrying the virus, and H is the population that does not carry the virus. V and H are just two different classes in the previous virus detection example. Or actually equivalent to say in that example, we have two classes, B1 and B2. But since it's just two classes, of course, we can just use V and not V to represent B and not E, not B. But if the number of classes is larger than 2, we need to apply such more general form of Bayes rule. All right, so hope until now, everything is still clear to you. So any questions so far regarding like how can we get such general form of Bayes rule when there are multiple beliefs? Yeah, maybe we can pause a little bit, take a 3 minutes break. After the 3 minutes break, we can come back. And also, yeah, if you have any question, you can just try to sort out and summarize so that, yeah, we can also try to make use of the 3 minutes break to collect some questions. All right. After the short break, yeah. Think that no question until now. Very good. Yeah. Then that means, yeah, I think everyone is following my pace to start in night-based model. Very good. Continually until now, starting from the very beginning, like a very simple rule of this base rule, we try to generalize it into like the multi-class. Then let's continue to think of new question. What if we have multiple pieces of evidence? Like here, suppose we have D pieces of evidence, like it can be E1, E2 until ED, impossible D pieces. Like note that in all the previous example, we only have one piece of evidence, E. It's either E or not E. Like for example, if we look at the virus, the evidence is just the test. Like the test results can either be positive or negative. So basically we only have like one piece of evidence. Or in this smoke one, the evidence is just smoke. Like it's either there is smoke or there is not smoke. But usually in the real world problems, we have multiple pieces of evidence. Like if we want to make some diagnosis, we need to check different symptoms of the patient, or actually we need to check the different testing results of such patients. So that means actually one piece of evidence is not enough. Possibly it's just we have multiple pieces of evidence, and suppose we have these D pieces of evidence. Then what will be the more general form of Bayes rule? Note that in this case, the numerator still remains the same. The numerator is always like the prior probability times this likelihood, but this likelihood now is meaning change. What is this E? For any possible E, we need to consider the different combinations of these D pieces of evidence. Like it should be some P E1 until ED given BI divided by such marginal probability, like the sum of all these P E1 until ED given BJ times PBJ. What does it mean? You can consider that, yeah, maybe let me give you a very simple question, a simple example so that you can possibly understand. Suppose now our problem is to animal classification. Okay, animal classification. And suppose now the belief B can be like we have B1, B2, B3. For example, we have cat, dog, bunny. We have the three classes, like B1 is cat, B2 is dog, B3 is bunny. And in order to decide whether an animal belongs to a cat or a dog or a bunny, of course, you need like multiple pieces of evidence, right? Now suppose the E is such a evidence set, like our first evidence is color. Our second evidence, for example, is size. Okay, just to make it simple, we just use these two pieces of evidence. Yeah, maybe to make it consistent, like B actually, so B can be come from such set. Then in this case, whenever you need to decide whether it's a cat or a dog or a bunny, basically you need to consider two pieces of evidences, like the color and size. This is the meaning of like we have multiple pieces of evidence. Like for example, the color can have like different values like red, black, yellow, brown. Like size can have like small, medium, large. Like each piece of the evidence have different values. Actually, if we consider these multiple pieces of evidence, we will make the problem very, very complicated. Like in the general case, just suppose we have these D evidences. These D evidences. Each of them is binary. That is for any of these for any EJ, for example, the EJ can only be true or false. Like we just consider like, okay, now suppose each of the evidence can only be binary, take binary values. Then in order to calculate one posterior probability, like in order to calculate this PBI given E, like what should we get? In this case, consider that, okay, first of all, we need to get this prior. Prior is relatively easier to get, but what about the likelihood? Like, sorry, just put it down. The likelihood for example, we know that it's consisting of like these D pieces of evidence. This is one likelihood, but like how many possible values of such likelihood? Like if you want to get like such likelihood, how many like possible likelihoods you need to get? Suppose like each of these evidence is just some taking binary values. Now we need to consider like how many possible number of combinations of these evidences, right? So know that E1 can be true or false. Then E2 can be true or false, and so on and so forth. Of course, the last evidence ED can be true or false. And then for such a likelihood like PE1 until PED, actually we need to consider all the possible combinations of their values to get likelihoods, because eventually like we want to get all this marginal probability. That means all the possible additions, right? Or that means for such likelihood, in total for such a likelihood, we have 2 power of D likelihoods, or 2 power of D like possible combinations of these different evidence values, right? This is what we have to consider. Like if we try to extend it to some multiple pieces of evidences, like all this is they can like take different values, or if we try to separate them, like for example, actually we need to get something like that, like E1 equals to T, E2 equals to T, so on and so forth, and ED equals to T, then given some BJ. This is the like one possible likelihood, one likelihood we need to get, and we always like can try to like split the value of any of these E, right? Because any of these E I actually can take true or false. So that's why in total we have like 2 power of D likelihoods. We need to know, we need to get these 2 power of D likelihoods in order to apply such naive Bayes rule in this posterior likelihood calculation. Of course, that is too complicated. The complication lies in that we should be provided with so many observations. For each of the possible combination of these D pieces of evidence, we need to get its likelihood. But in reality, we cannot make so many possible like observation to get all the likelihoods we want. And even if we have, then the calculation of such posterior likelihood will be like too complicated. It's some exponential items we need to add up. And that's why, and that's the motivation of the naive Bayes model. We try to simplify the calculations of such general form of this Bayes rule. And let's look at what is the naive Bayes model and why it can try to simplify the calculation. So now in order to simplify the calculation, we made assumption. After adding the assumption, all the complexity will be reduced. What is this assumption? Here we simply assume that each piece of evidence, they are conditioned independently and equally contributes to the probability of a sample belonging to a certain belief. This is a very naive assumption, and basically that's why the Bayes rule is referred to as a naive Bayes when we make such an assumption. In other words, now the presence of one particular evidence in a belief does not affect the presence of another one. Like even though now we have like multiple pieces of evidence, but we just assume they are all conditioned independently with each other. Here, two keywords, of course. First, conditioned independently. Second, equally contributions. Let's try to explain these two assumptions one by one. First, what do we mean when we are saying they are conditioned independent? So here is an example. Given a certain outcome, for example, our belief or this outcome is whether to go for a walk or not. And we may have different pieces of evidence. For example, temperature is one evidence. Humidity is another evidence. Outlook is the third evidence. But we assume all these evidences are conditioned independent given a certain belief. So that means if we already know a certain outcome, we already know that the label or the result, the belief is going for a walk, then the temperature being hot has nothing to do with the humidity being high or the outlook being rainy does not affect the winds. The wind is some another evidence here. So basically is that all these features are assumed to be condition independent given a certain belief. And yet pay attention to this conditional independence. Conditional independent, basically it's possible that these features or these evidences, they are not independent with each other, but only after given a certain belief, they becomes conditional independent. Because this may get like sometimes may get confused. So yeah, pay attention to that. Like independence and conditional independence are totally two different things. So you need to get clear. The evidences may not be independent with each other, but they are conditional independent with each other. Given a certain belief. This is a conditional independent. The second keyword here, we say that, okay, all these evidences should have equal contribution. Equal contribution basically means that each evidence must contribute to the outcome, equally contribute to the outcome. We cannot let it happen that some evidence basically does not have any effect on the outcome. Like here is an example. Knowing only temperature and humidity alone cannot predict the outcome accurately because there are some other beliefs, some other evidences. Like for example, we also have the outlook, we also have the wind. Like all these evidences, they must contribute equally to the outcome. Like we cannot let only like one or two evidences to decide the outcome if there are some other evidences also. And these are basically assumptions made by the naive Bayes model. Yeah, hope that would be clear to you, like conditional independent and equal contribution. Note that we must claim that actually the assumption made by naive Bayes are not generally correct in real-world situations. And in fact, such conditional independence assumption is never correct. Basically, it's a too naive assumption. Like, just take this example. Like, we know actually, even though we are given a certain outcome, even though we know like the result is going for a walk, actually the temperature and humidity are they really conditional independent with each other? maybe by some real world experience, you find no, right? You find actually it seems the two evidences have some relation with each other. Yes, actually it's your sense is right, because such conditional independence assumption is never correct in real world. Then why are we still using naive-Bayes model if the assumption at the beginning is wrong? One reason is that the naive-Bayes model often works very well in practice. That means even the assumption is not correct, but the results are usually correct. Like using the naive-Bayes model to the prediction, the performance is very good. But of course, I know you won't be satisfied with such explanation. Like if in theoretical it's not correct, then what's the meaning, what's the use of like working well in practice? So no worry, at the end of the lecture, like at the end of the naive-Bayes lecture, I will explain to you that why, like maybe some more inherent reason, like why naive-Bayes model works well in practice, even though the assumption is wrong. So now just keep this question in mind, and let's see, after making the assumption, what have changed in the Bayes rule. Now, everything gets very, very simple because we know each evidence makes some conditional independent and equal contributions given the belief. So we just try to transform it to the following. Previously, we know the likelihoods is very complicated. Each of the likelihood is something like that. P E1, E2 until ED given BI. And we know like such E1 to ED, like for example, if it's binary, it actually has like exponential terms, like 2 power of D terms. But now doesn't matter because they're conditionally independent with each other. Conditionally independent with each other means that this PE1 to ED given BI is exactly equal to this one. PE1 given BI times PE2 given BI. Like just transform it to a multiplication of all these D single likelihoods. It's no longer like combination of the evidences likelihood. It's some single likelihoods multiplying together. This is the property of conditional independent. And of course, for the denumerator, previously is the sum of some like likelihoods, the combination of evidences, but now everything gets very simple because this one is exactly the multiplication of some single evidences. Yeah, this is the magic of conditional independence. After making the assumption, we just made the calculation so simple. And then let's check like now how many likelihoods we care about. Again, suppose like all of the evidences just take binary values, they can either be true or false. Then how many likelihoods do we need now? Consider like PE1 given BI, only 2, right? Because it's like E1 can only be true or false. So basically we only need 2, like PE1 being true given BI, PE1 is false given BI. And similarly for this one, PE2 given BI, we have 2 likelihoods. We need to know that. And in total, we have D pieces of evidences. So if in this case, like if for binary evidence, or suppose all the pieces of evidence just take binary values, we need 2 times the likelihood, right? Because for each of the single likelihood, we only need 2 likelihoods. Compare with the previous one. Previously, we need 2 power of D, some exponential. Now we only need 2D likelihoods, it's some linear number. That's why now the computation, all the computation and also the memory gets reduced a lot. So all the calculations, the model is simplified a lot. And basically that's a big motivation to do such naive assumption. Now to transform the previous very complicated Bayes rule into a naive Bayes rule. But here let's consider another question. So let's try to apply such naive Bayes model in the practical classification problem. In classification problem, we are given a test data sample. This test data sample is with evidence E. And in classification, basically, we want to know which belief or which class it belongs to, right? We want to classify this test data sample into a class. So we calculate, okay, we calculate the first posterior PB1 given E, and then calculate PB2 given E. At the end, we calculate PBN given E. Like in total, we have these N classes. And what would be the next? Next is we will compare all these N probabilities, right? And we will classify the test data sample into the class with the largest posterior probability, with the highest probability. In this case, like when calculating this posterior probability, possibly for each of them, we follow the above naive Bayes rule to calculate, and then we calculate this N. Here the question is, do we need to strictly follow the formula and, here is a typo, and calculate the actual probability values. Sorry, a typo here. Calculate the actual probability values. Here is a question. Maybe you can try to think about. But just now I received a new question in chat box. Is that why was it 2D likelihoods instead of D? Yes, actually 2D. Like in asymptocy, they are the same. Actually, if you see that D likelihoods is also correct, because we know that basically E1 even BI, for example, the E1 is false given BI equals 1 minus E1 being true given BI. So yeah, if you say that is D likelihoods, that's also correct. So theoretically speaking, we need 2D likelihoods, but of course, according to the total probability rule, this 2D likelihoods is exactly D likelihoods, right? Because if we already have this one, this one, we can simply get this one by like 1 minus this one. Yes, very good question. Thank you. Another question, no, this one is, if we make the naive assumption, then basically in this formula, we only need 2 times the likelihoods. But previously, if we do not make such naive assumption, then we need to power of the likelihoods. They are totally different cases. Because in this case, we don't have the assumption that they are conditionally independent. Then for each of these, as you can see, PE1 until ED given BJ, we have to calculate something like this. For each of the possible values for this E1 to ED, we need to calculate the likelihood. So in this case, it's 2 power of the likelihoods. But of course, know that if we follow previous one, this is exactly like just mention more, since you are interested in this one. Actually, we can just use 2 power of the minus 1 likelihoods to represent what we want, to store all the likelihoods what we want. Yeah, I hope you know the reason, right? The reason is that actually among these 2 power of the likelihoods, they must add up to 1. So basically the last one is just you use 1 minus all the previous likelihoods, you can get 1. So that's why actually to when really like do the, for example, do this likelihood storage in your memory, maybe possibly you just need this 2 power of the minus 1 likelihood, because anyway they add up to 1. But in this case, after make this conditional independence assumption, we only need 2 times the likelihoods. And among these 2 times the likelihoods, actually, in order to save the memory, we just need this D likelihoods. Another student asks is whether it's 2 power D minus 1, like inside the parentheses, or 2 power of D, then minus 1, the latter, this one, 2 power of D. First calculate this one, then minus 1. Because these 2 power of D likelihoods add up to 1. So you can only omit one because you can use one minus all the remaining likelihoods. So like in memory storage, you just need to store this 2 power of d minus 1 likelihoods, the latter. Yeah. Yeah, it's great that you think more about like the likelihoods thing. Okay. Very good. Yeah, hope this would make sense to you. And if you have any more questions, please feel free, just type in the chat box. In the meantime, I will continue with like here this question. Anyone already get a reason? Like, do we need to strictly follow the formula and calculate the actual probability values? That is for each of these P, B, I given E, do we strictly follow the formula? Actually, no need. Why? Consider that now what we want is not posterior probability, right? When doing the classification, what we want is the classification results. We calculate the posterior probability only in order to compare them and select the highest probability to do the classification. But that's not our ultimate goal. Ultimate goal is classification. Ultimate goal is not probability. So, excuse me for a second. So that is to say, in a real machine learning classification problem, we are only interested in knowing which belief had the highest probability value rather than the actual probability value. In that case, actually, we can further simplify the equation by removing the denominator. Like now, the p-naive bias, here the p-naive bias means that the belief that will be selected or will be predicted by the naive Bayes model actually is the argmax of PBI times the multiplication of all these likelihoods. If you look back at this formula, you will find that basically is we only calculate the numerator here, right? We only calculate the numerator part for each of the beliefs and select the max. Why? Because if you look into the denominator, they remain the same for all the beliefs. The denominator here is basically the sum of the likelihoods times the prior, and the sum is j from 1 to n. So j from 1 to n, what is j from 1 to n? That for each of the belief, we get this thing and then add them up. So this denominator thing is the same, remains the same for all the beliefs. Basically, it's a normalization term. It's the sum of all the numerators of each of these PBI given E, right? This is one numerator. And if you consider like all the numerators of B1 until Bn and add them up, they are just exactly here in the denominator. This is a normalization thing to make sure that all these probabilities add up to 1. Yes, that's why we say here, because the denominator remains constant for a given input. For any beliefs, it just remains constant. So if you want to compare like who has the largest posterior probability, basically it's equivalent to who has the largest numerator. So that's why we just put the numerator here. It's fine. We simply only calculate the numerator and compare who has the largest numerator and then assign the class. All right, actually, we try to simplify the model further and further, right? First, by make some assumptions so that, okay, we only need all this conditional independence, the single likelihoods. After that, we just simply drop out all the denominators. We don't want the denominators, we just calculate the numerators. But now we have another question. This is a question that it's like actually it's commonly happen when we are doing the naive Bayes model, use it to do the testing, to do the classification, is that consider a feature EJ. Yeah, Note that actually now we already call it feature, but this feature is exactly evidence. Like usually it's in Bayes' rule or in statistics, like the statistical mathematician call it evidence, but in our machine learning, we just simply call it feature. They are the same thing. Now consider such a feature EJ. And suppose EJ has m possible values, like EJ can take the values v1, v2 until vm, and then for each single likelihood, like PEJ equal to VK given a belief BI, according to the conditional probability formula, we know that this one should be the probability of EJ equal to VK and BI divided by the probability of BI, right? This is the definition of the conditional probability. This is the likelihood. And again, we know that usually the probability just comes from the count of the corresponding events. So we count, like we first get a count of like how many times we have such events like EJ equal to VK. In the meantime, it's a belief BI, and then divided by the count of BI. Basically, it's how we get a likelihood, right? Observing some events and count the number of events, get the likelihood. But here is an example of the question: what if in our training data, we have never made the observation of EJ equal to VK and BI? So that is, what if in our training data, the count of EJ equal to VK, BI equal to 0? It's possible. Note that it's possible. It's possible because usually it's possible that we do not have enough number of observations. Like we only have some limited collection of all the training data sample, then it's possible that we do not make such observations, or it's simply because such events happens with a rare frequency, but still it has a very small frequency that we haven't observed it. So anyway, due to our limited data collection, possibly in our training data, the count of such event is 0. Then according to this formula, we need to assign 0 to such likelihood, right? If we get the count of such event is 0, then the numerator is 0, then the probability is 0. But note that if we directly assign 0 to such likelihood, then the prediction might be very inaccurate. Because if the test data has such feature, like the testing data EJ equal to VK, then if we simply assign the likelihood of such one to 0, then that means basically this numerator later on will become 0, right? If one of these likelihoods, as you can see, becomes 0, then the total multiplication, of course, becomes 0. Then it might be some inaccurate estimation. In this case, we want to solve this problem. Then basically, the idea is that we don't want to assign 0 to any of the likelihoods, because eventually we don't want to have some 0 posterior probability. How to address this one? We have a technique, it's called alpha Laplace smoothing. The problem, if we state it here formally, the problem is called zero frequency problem. Zero frequency, of course, is that the frequency of some event becomes 0. So if the category feature has a category in the test data set which was not observed in the training data set, then the model will assign a 0 probability and will be unable to make a prediction. This is known as zero frequency. The solution here is we apply alpha Laplacian smoothing. Here is the idea. Simply pretend you have seen every value of the feature given every belief alpha more time than you actually did. So previously, the probability PVJ equal to VK given BI is the count of such events divided by the count of BI. Now, pretend that for each of the possible values of EJ, you observe it with alpha more times. So that the count of such EJ equal to VKBI never becomes 0. Basically, it's this thing. like the count of EJ equals VKBI now plus it with alpha, because now we pretend, okay, for each of the possible event, we just observe it with alpha more times, so we should add alpha here. Don't forget the denominator, because you add something in the numerator, then basically in the total possible cases, you observe more times. So the denominator, the count of BI, we need to add it with m times alpha. So here m is the number of possible values of EJ. Basically, is we still follow the assumption here that EJ has m possible values V1 to Vm, and then in the denominator we need to add m times alpha. Here, alpha, how to take its value? Usually, like for simplicity, we just let alpha equal to 1. Or it's called 1 Laplace smoothing. It does pretend that you have seen one more time you actually did. But note that it's not always that like letting alpha equal to 1 is the best case. Usually we see alpha as some hyperparameter. So that is impractical. Usually we will tune this hyperparameter to select the best values for alpha. But I believe you have one question possibly, is that why the denominator, we need to add m times alpha. What is the reason? So I would like to leave this as an after class question for you as practice. So maybe you can take some time to try to think about why this denominator thing we need to add m times alpha to do such smoothing. And in next class, at the beginning of the next class, possibly if you have any idea, you can just tell me at the beginning of the next class, and I will also explain the reason and try to elaborate clearly of this alpha Laplace smoothing in the next class. Receive a question, what does argmax mean? Does it mean which belief had the highest probability? Yes, exactly. Argmax, okay, if this is the first time that you see such function called argmax, maybe I can define what is argmax. We see that if in general form, if x is argmax, maybe let it be x star be argmax or x, and with the function fx. This argmax function means that x is the value of x such that f x star larger than or equal to any possible fx. Basically, is x star is the value of x such that fx star is the maximum possible value of fx. Yes, so your explanation is correct. BNB, okay, BNB is the returned belief of naive Bayes model. So the naive Bayes model will return such a classification result by selecting the argmax. Yes, thank you for your question. Okay, you're welcome. So basically that's the end of today's class. Any other questions? Great. If no other question, don't forget that lab 2 has been released. So basically, actually, until now, with all today's lecture contents, that's already enough for you to start to do lab 2, actually, the lab 2 task. And for LA2 students, don't forget to attend the lab 2. 10 minutes later, we will still take your attendance on that Zoom meeting. And everyone, please stay at a safe place. And please take care and stay safe during the very bad weather. And hopefully, if the weather allows, I will see you in campus on this Thursday. But if the weather is still bad, then possibly we may still need to have some online classes on Thursday. But let's see. So hope everyone stays safe and see you next time. Bye-bye. Bye. Thank you.
Thank you. Have a nice day.
Thank you. Have a good day.